So today I'm going to introduce two kinds of methods to remove multiples as a topic today. And this is the outline of my presentation. First, I will introduce how to classify multiples. Then I will go through two kinds of methods called model-driven and data-driven methods. Then I will show you some case studies. And I'll be happy to answer your questions and discussion. So basically, there are two kinds of multiples, depends on the way multiples are generated. One is called surface-related multiple, the other one is internal multiple. The difference is for surface-related multiple, we should have at least one point where the seismic wave will reflected at the surface. So you can see here, we have a downward reflection happens at the surface. So in the whole rate path of multiples, you have at least one point happen at the surface, then it's surface multiple. Otherwise, it's called internal multiples. So we need to have different ways to handle these multiples. So based on the way we to remove multiples, there are two kinds of methods. One is rely on the velocity difference between the multiples and primaries. So if the velocity difference is big enough, we can rely on velocity model-driven methods. For example, after animal correction, the primaries are flat and the multiples are curved down. Then we can use stacking to emphasize the primaries. So, naturally, the multiples will be suppressed. That's a very conventional way, it's a very robust way. Or we can use a parabolic radial transform to focus seismic signal in a different domain, a so-called radial domain. And in this domain, both primaries and multiples are well focused and are well separated because of velocity difference. Then we can design a mute and come back to the time and space domain, then subtract multiples. Or without animal correction, we have good velocity model. We can use hyperbolic radial transform. And the benefit is we don't need to worry about the animal stretch. That's an advantage of the hyperbolic radial transform. So if the velocity difference between primaries and multiples are small, then this kind of velocity model-driven methods will be compromised or fail. Then we resort to data-driven methods. So totally data-driven, we don't need to use have a good velocity model to estimate the multiples. So, for example, the conventional gap decount, we can usually to remove the short period multiple. We can predict the multiples by applying a time delay to the input and then trying to find a good filter to match input, so we can remove multiples. Or we can use for longer period multiple, we can use SRME, is a so-called surface-related multiple elimination. This is to trying to remove a surface-related multiple. Or for shallow water multiple, we can use a model-based water layer multiple. I will explain in a minute the difference between SRME and MWD. For the internal multiple, we have two options. One is called IME, internal multiple elimination, and ISS, inverse scattering series multiple. We're going into details. So in recent years, we have a collaboration with primary geo services to develop a suite of multiple tools that can handle both land and marine data, both 2D and 3D data, and for short and long period multiples. So if you're interested, please welcome to visit the website for more details. Now let's first look at the model-driven methods. So there are many model-driven methods today. Because of limited time, I will focus on a new development to enhance the conventional radial transform for higher resolution. So as I mentioned, in this kind of velocity model-driven methods, we rely on the difference between primaries multiples in velocity. First, we convert seismic data to radial domain to separate multiples from primaries. The resolution of the radial model is the key to the success of these methods. So in our development, we'll have greedy methods to enhance model resolution. So this is basically a problem we want to solve. So this is a cost function we want to minimize to acquire a high resolution radar model. So on the left is the cost function of the model, M is a model, and D is the seismic data, and we have L is the modeling operator, which converts radar model to seismic data. M is a model, so you can see we are trying to fit the seismic data using a simple radar transform. And we also, to make the solution stable, we need to introduce a regularization function to the radar model. Depending on the kind of model regularization we use, we have different kinds of solution. If we use a L2 norm for the R, the regularization, the solution is smooth and low, has a low resolution. If we use L1 norm, it's higher resolution. But in our development, we use a prioritized L1 norm methods, so-called greedy methods. It will give you a super high resolution. I show it with a simple synthetic example. So this is a synthetic that I want to show. You can see in this, on the left is the input data. We have a series of flat primaries, and we have some slightly curved down multiples, which pose a challenge to all kinds of pre-multiple methods. So in the middle is the result. The estimate model use the L2 norm methods. You can see a lot of leakage for the primaries. On the right is the output demultiple. Certainly, we don't like this result because of primary leakage. This is the result from L1 norm methods with a sparse constraint. Definitely, we see a lot of improvement. We see the leakage of primaries has been minimized compared with L2 norm methods. But still, we can see leakage. How much can we improve? So we can use some more. With the greedy methods, you can see. So the leakage is much smaller than the L1 norm methods. So to explain why these methods can give us better solution, this is a plot of the radar model. So on the left is the so-called L2 norm methods. You can see a lot of crosstalk between primaries and multiples. You can see the top P is the move out on the P domain. You can see, so if it's flat, the move out is supposed to be 0. But because of the resolution limit, you see it's crosstalk with the multiples. So you can see almost like a one event, although actually 2 events. In the middle is the L1 norm methods result. We see it's improved. So here is well resolved, but at this location, you can see still it's difficult to separate primaries from multiples. So on the right is the result from our new methods. You can see we successfully separate multiples from primaries clearly. There's some challenge here, but still better than the conventional methods, L2 methods, and L1 methods. So you can see the well separation of multiples and primaries at this spot. Now, let's move on to data-driven methods. As we mentioned, when the velocity difference is too small, then velocity-driven methods will fail. So this is we rely on these data-driven methods. So in this kind of methods, we partially or totally it's totally driven. It's not dependent on the velocity difference. We have developed most popular evidence, including gap decount, SRME, MWD, IME, and ISS, etc. So today I'm going to share with you the experience we gained for these 4 methods: SRME, MWD, IME, and ISS. So basically, these 4 kinds of methods can be explained in a unified ray theory if we consider the ray path of the multiples. So for example, for the surface-related multiple, you can see in this simple example cartoon, we see 2 segments in the ray path of the multiple. So we have source here and receiver here. It hit the surface and get rebound and going down and reflected at the subsurface and go back to the surface. So we can have 2 segments. So you want to compute the contribution of a multiple the location for one contribution, we actually take the corresponding seismic trace from source to this reflection point, and then we have a second source from the reflection point and to the receiver. So we have two seismic traces. We convert these two traces together to get one multiple contribution. So this is the ideal situation where we know the exact location where the reflection happens, but we actually in the real world we never know the answer. That's why we need to try all the possibilities along this line. So there are a lot of combinations of reflection points. Then we sum together all the contributions to predict one model multiple trace for this kind of geological setting, source here and still here, and repeat this procedure for all the pairs of source and receivers in a seismic survey. So this is a 2D example, but it can also be extended to 3D case. And in 3D case, we have a summation surface instead of a summation line. So in the MWD, so-called water layer, model-based water layer departmentable. In this case, when the water layer is too shallow, so the near offset data is not recorded because the typical distance is already past the critical angle for the shallow water layer. In this case, the good news we have the water layer model. Then when you get this model to analytically compute the travel time, the green function from source to the reflection point, that means we can actually replace this seismic data with green function, and we can do the convolution and the summation similar to SRME. So advantage is we fill in a gap that is not recorded in the seismic survey for shallow water area. So the IME is trying to address internal multiple problem. Here, you see similarly we can just decompose the ray path into several segments. You can see we have a red segment and green segments. So actually we can pretend we have some ray paths and above the generator, we have two reflection points, C1 and C2. Then we can do this math, combine the ray path from S to this reflection point and go back to the surface to C1, and have another ray path from C2 goes down to the subsurface and go back to the surface. So actually, if we sum up the time, the ray paths together, we have two redundant ray paths, which is from C2 to this generator, and from this generator to C1, the other reflection point. So we need to remove this redundant ray paths, which in mathematically can be done by applying a cross correlation between the result of convolution with the ray path from C1 to C2. So we can eliminate the redundant travel time, which is actually a correction in a full domain of just phase correction. But the downside of this method is we need to pick the multiple generator, which involves an interpretation of the seismic data. We know what are the major multiple generators. So in the end, the fourth method is called ISS, inverse scattering series. It's a method proposed by Arthur Wegland from University of Houston about 20 years ago, almost the same time as SRME. It's actually, based on my understanding, is equivalent to applying internal multiple elimination multiple times. So how many times? So actually, for ISS, theoretically, we need to calculate the contributions for all time samples. So each time sample, we think all the events at each time sample can be regarded as a multiple generator. So we apply IME for each time sample, which is super expensive. But we have in our implementation, we have jigs to reduce the runtime to make it practical. The good news is there's no need to pick multiple generators because we actually predict multiples, all possible multiples by applying IME to each time sample. So in summary, we have surface radar multiple solution, which are S.A.S and MWD, and for internal multiples, we have IME and ISS. Now let's go into the exciting part of this talk. Let's see some case studies of our own methods. So first case is for greedy radon transform. And this is from marine survey. I think I built some short gathered out animal collection for QC purpose. So this is the input to the algorithm. And this is the output. You can see it's quite nicely remove the curve down multiples and preserve primary nicely. That's the difference. Input, output, different. I repeat 2 times. Input, output, and difference. And second example is 2D MWD, which is coming from Canadian coast, I think. So you can see the water bottom is around 300 milliseconds, and near offset is 285 meters, which poses a challenge to the conventional SRME algorithm, because in SRME we need to record data at the near offset, which is missing. This is a very old survey. We don't have near offset. So this is the input channel, and this is the result after MWD. You can see certainly a lot of ringing and repeating patterns, which are most of them are multiples. So input and output. So after the multiple, you can start to see the sort body, which is nice. Otherwise, it's challenging to interpret the geology. So the third example I want to show is a 2D SRME result. This is short gathers before SRME, and this is after SRME, before, after. So at the near offset, see some residual, but we can remove this residual using other methods afterwards, like radon and deflection multiple attenuation, which I will show in a few minutes. And this is stack before SRME, and this after, before, after, before. Obviously, you can see these are repeating shape of the surface. Let's see, so after SRME, it's nicely remove that, so that we can interpret the geology pattern. So this the fourth example is a 3D land survey. We have applied SRME and IME in a cascade way. So this is the input stack. In the middle, on left, you can see this is a corridor stack from VSP data, in which we don't have multiples, and this can be used as a reference to know if we are doing a good job for multiple attenuation. So in land data, usually it's more difficult than marine data because it has a lower signal to noise ratio and has a poorer spatial sampling, and also you have a surface topography. These are major challenges to applying data-driven methods to multiple. So this is the input stack, and this is after SRME. So I would like to draw attention to this area. You can see these are very strong multiples. So it's difficult to tie with the VSP stack. After SRME, we certainly improve a lot on the VSP time. And this is after IME. So IME, you can see some multiples here, attenuated in this area. After. So without the multiple, the client said they will not be able to conduct avial inversion and AVAC inversion. After this, the multiple, they finally get some results. It's really helpful for them to interpret the reservoir. This is a fifth case study showing the combination of SRME, radon transform, and diffracted multiple attenuation. this is a very nice job from my colleague. She used our tool and a lot of experience to have this to achieve this results. So this is the input stack, and this is the after all the multiple tools we have used this. So very nicely, we can see the structure going through from shallow to deep, before and after. So this is another survey nearby, and we have a stronger variation on the water pattern. So that will introduce some geographic multiple. Like here. So this is the input stack and this output stack. It looks very clean and doesn't touch the primaries. So last example I'm going to share with you is a recent process data using the ISES methods. It's a land data. So you can see, so this is a non-conformity. Above the non-conformity, we see a lot of shale, very thin layers, which generate a lot of ringing in the basement. So the clients are concerned about the area near the non-conformity. So before the multiple is difficult to interpret because of ringing, and it's very annoying problem in many areas. So this after the multiple, you can see certainly will greatly improve the interpretation after the multiple. Before and after, this difference. So it's nicely removing the ringings. In the meantime, it doesn't touch a lot the primaries. So it's a nice interpretation on the structure, geology structure here, before and after, and difference. So in conclusion, so really we can see the multiple can greatly improve the interpretability of seismic data. And we have developed a suite of effective multiple tools and were tested by real data. And thank you for your attention. I'd be happy to answer your questions.